Hello everyone, today I will be talking about my project for EEE474 574 Foundations of MRI class. And my project is to implement echoplanar imaging trajectory with spin echo pulse sequence using MRI Lab sequence generator, since MRI Lab only provides EPI for gradient echo sequences. Before I talk about the implementation details, I want to give a brief summary of the related topics. The reason why we require gradient or spin echo is that the original free induction decay signal decays too rapidly for necessary amount of signal sampling. Gradient echo is produced by a single RF pulse with a gradient reversal. In contrast, spin echo uses a second 180 RF pulse to rotate the plane of the magnetization spins to achieve signal refocusing. Since only one RF pulse is applied in gradient echo time TE is generally shorter than the spin echo sequences. Short TE values also provide more rapid image acquisition with only one RF pulse. However, it refocuses only the spins that have been dephased by the dephasing gradient, so its signal does not decay with T2 but at a higher rate of T2 star. In API pulse sequence, the phase gradient is blipped with short magnitudes, while the frequency gradient is a higher frequency rectangular, trapezoid, or a sinusoid waveform that is switched between negative and positive amplitudes after each blip of the phase gradient. The resulting key-space trajectory resembles a zigzag. Before I implemented the spin echo API, I experimented with the existing one for TE 24 milliseconds and TR 4000 milliseconds. The contrast is achieved with the flip angle, since gradient echo does not require 90 degrees flip angle. For T2 weighting, we can see that the CSF is more bright as well as the gray matter. And also the white matter is darker than the T1 weighted image, as you can see here. In this section, I will explain the implementation details and perform a sample imaging simulation with the designed pulse sequence, and lastly propose an extension. Firstly, we need to add a second RF pulse, that is TE over 2 apart from the first one. Each pulses have 3 millisecond length, and second RF pulse has pi over 2 phase with 180 degree flip angle. Here you can see the RF pulses in pulse diagram. For TE 24 milliseconds, you can see that the second RF pulse is placed at 12 milliseconds, so the design is correct. For Y gradient, we need to place it after the second RF pulse, so additional shifting is added to T1 start and T2 middle. Here CV1 is just a variable so that it can be changed in the main control panel. Similarly, X gradient is also shifted after the second RF pulse, and ADC is adjusted accordingly as well. The overall pulse sequence looks like this for one TR, and the covered key-space trajectory looks like this. I performed imaging for TE 24 milliseconds and TR 4000 milliseconds. I also calculated CV1, CV2 and RF pulse lengths accordingly, so the variables may not be suitable for every TE and TR value. And for example, when we decrease the TR, we see Nyquist ghost aliasing. With even lower TR, we see ghosting occurs even more. In order to reduce the ghosting, I decreased the API shot number, which refers to the number of K-space lines collected in a single shot of measurement. Aliasing is gone, but the resolution has gotten worse. And I also investigated why the ghosting happens. The Nyquist ghosting artifact happens when even and odd echoes are not perfectly mirror of one another. Even a simple delay at the start of the first echo will result into preceding even and odd echoes. And when the image is Fourier transform, phase error results in signal intensity displaced in the phase encode direction halfway across the image. And you can see that the half images are replaced in the original field of view. Lastly, I performed a simulation for different TE values to see the effect of TE over TR to observe the effects on the image contrast. With longer TE, we can see that the contrast is leaning over to more T2 weighted. We understand this from CSF and gray matter being brighter. As an extension, I also tried an unblipped version of the API trajectory, but I haven't got the time to test it. The only difference is the phase encoding gradient is a constant rather than blipped. The covered case-based trajectory is as follows. And thank you for listening.